Right before your eyes is one of the busiest and most massive infrastructure construction sites on the planet, the Navi Mumbai International Airport project. With a total investment of up to $2.36 billion, equivalent to over 19,000 crore rupees, this mega construction site covers a massive area of 1,160 hectares. This super infrastructure includes core components: two independent parallel runways, each 3,700 meters long, a continuous dual taxiway system, and a central terminal directly integrated with an underground railway network. The ultimate goal is to create an aviation hub capable of serving 90 million passengers per year. However, to build such a massive system on complex terrain, engineers had to solve two extremely difficult physical challenges: completely demolishing and removing a 116-meter-tall solid rock mountain, and diverting the flow of a large river cutting right through the core of the site. So, how did the engineers completely reconstruct the natural surface of this area? In today's video, let's break down the project to find out the details. Before we begin, don't forget to hit the like button, subscribe to the channel, and hype up this video. And now, let's get started. $2 billion is a massive investment just to kickstart a project. This decision did not stem from a normal expansion ambition, but as a mandatory solution to an ongoing infrastructure crisis in Mumbai. The economy of India's largest financial center is being held back by its current international airport. When observed from a satellite map, the entire perimeter of the airport is surrounded by dense residential areas. The empty land for expansion has been completely exhausted. However, the biggest technical reason forcing the government to spend money on building a new one, instead of upgrading, lies in the geometric structure of the runways. The old airport operates with two crossing runways. According to aviation safety standards, this intersecting design does not allow planes to take off and land in parallel at the same time. Whenever a plane moves through the intersection, the other runway must temporarily halt all operations. This design limitation sets a maximum ceiling on the number of flights per hour. No modern radar technology or dispatch system can overcome that physical barrier. When the old infrastructure has reached its absolute peak, further upgrading is useless. That is when the economic and technical problems meet. Accepting a cost of $2 billion to recreate a complex terrain 35 kilometers away from the center is the only feasible option to establish an independent aviation infrastructure with two parallel runways, completely solving the travel needs of tens of millions of people. Skipping the planning steps on paper, right when the machinery entered the 1,160-hectare land, engineers immediately faced the biggest physical obstacle of the project: the 116-meter-tall hard rock Ulwe mountain sitting right in the middle of the site. Sitting right on the planned location for the runways and core terminal, this mountain could not be bypassed. The only way was to wipe it out completely. The cutting process was carried out using controlled drilling and blasting techniques. Because the site is located quite close to existing residential areas, engineers could not use a large amount of explosives all at once. Instead, they set up an extremely detailed drilling and blasting coordinate grid on the mountain surface. Explosives were placed in deep drill holes and detonated in a delayed sequence measured only in milliseconds. This delay-action blasting method helped break the hard rock structure from the inside, but canceled out the shock waves and minimized tremors transmitted through the ground. After each blasting phase, the mountain was shaved off layer by layer from top to bottom. Immediately, a fleet of hundreds of excavators and heavy dump trucks moved in, working continuously day and night to clear the site. The technical goal was very clear: lower the absolute height of this entire geological mass from 116 meters to a flat surface at an elevation of 8 meters above sea level. After many months of construction, the total volume of rock broken and removed reached over 20 million cubic meters. This massive amount of material was immediately transported by the truck system straight to the adjacent swamp area, opening up the second technical construction step of the project, surcharging and draining the weak soil foundation. In this saltwater swamp area, the original soil contained a huge amount of groundwater, making its mechanical load-bearing capacity almost zero. If asphalt or concrete were poured directly, the weight of wide-body planes would instantly cause uneven settlement, completely destroying the entire foundation structure. To squeeze the water out of hundreds of hectares of soft mud, engineers applied the prefabricated vertical drain method. A series of specialized machines moved in, inserting hundreds of thousands of drain strips through the mud layer, deep down to the hard soil layer below. Right after that, the massive volume of rock from Ulwe Mountain was piled high on the surface to add weight. Under the massive gravity of the rock layer above, an extreme compression pressure was created, forcing the water inside the mud foundation to move up along the drain strips to the surface. The collection trench system would pump all this water out to the sea, tightly squeezing the soil particles together and completely eliminating excess settlement. However, consolidating the soil foundation could not complete the entire surface without solving a huge hydrological obstacle, the Ulwe River. This natural flow cut directly across the position of the southern runway. Engineers could not fill the old riverbed while a massive volume of water was still flowing. They were forced to bend this flow at a 90-degree angle. In terms of fluid mechanics, when forcing a river to turn, the entire volume of water carrying great kinetic energy will crash straight into the outer bank of the corner, creating a highly destructive hydrostatic pressure. To control this power, first, engineers dug a new 200-meter-wide artificial channel entirely on dry land. At critical corners, a steel sheet pile system was driven through the mud by vibratory hammers, pinning tens of meters deep into the bedrock structure. This deep anchoring structure acts as a solid pile foundation, holding the channel banks tightly to resist shear forces and completely prevent underground erosion. At the same time, the slope of the channel bed was set accurately based on a digital elevation model to ensure the flow velocity reached a balanced level, not too slow to cause siltation and not too fast to erode the channel bed. Only when this new channel reached its maximum load-bearing strength, the river diversion process began. Cofferdams made of steel and rubble were dropped into the old river, slowly narrowing the cross-section and forcing the water flow to shift to the new channel in a controlled manner. When the original flow was completely locked and the old riverbed dried up, trucks then continued dumping rocks to fill it, officially locking in a seamless, super load-bearing flat surface. When the foundation reached its absolute static settlement threshold, the project entered the phase of pouring the runway surface and assembling the core terminal architecture. The two 3,700-meter-long runways were constructed following a multi-layer load-bearing structure to cope with the extreme impact forces from super-heavy aircraft landing at speeds of over 250 kilometers per hour. On top of the force-dispersing crushed stone base course is the high-strength reinforced Portland cement concrete surface. The expansion joints were calculated precisely down to the millimeter using stainless steel dowel bars, ensuring the road surface expands safely under the Indian heat without generating cracking stress. In parallel, the lotus-shaped central terminal structure, designed by Zaha Hadid, was also taking shape. Behind the aerodynamic shell is a complex space frame steel structure. To completely free up the interior space, engineers used a high-strength steel beam system with long spans, eliminating concrete support columns as much as possible. This massive roof system self-balances lateral thrust forces, transfers the load down to the perimeter support pillars, and is strong enough to withstand cyclones from the Arabian Sea. From a complex saltwater marsh terrain locked by rock mountains and rivers, engineers thoroughly applied delay action blasting, fluid mechanics, soil mechanics, and space structures to completely recreate the physical surface. In fact, Phase 1 of this super infrastructure officially went into commercial operation at the end of 2025, and expansion phases are still being constructed continuously. When the entire life cycle of the project is completed, Navi Mumbai International Airport will not only be the definitive solution to the air traffic limit problem of India's largest economic center, but also an absolute technical proof of the ability to shape nature, establishing a mega transit hub connecting South Asia directly with the global transportation network. Our video today comes to an end here. If you have any questions about any stage of this construction, please leave your thoughts in the comments section below. Thank you, and see you next time.